Imagine a wall, not of bricks and mortar, but of light itself, completely obscuring the universe's earliest moments. That's essentially what the cosmic microwave background, CMB, is, and it's preventing us from directly observing the universe's most formative period. But don't lose hope. Scientists are exploring clever ways to peek behind this veil. So much happened in the universe's infancy: the birth of elementary particles, the creation of the first hydrogen and helium nuclei, and the energy fluctuations that seeded galaxies and supermassive black holes. Yet, direct observation of these events remains impossible. When we gaze into the distant universe, attempting to peer further back in time, our vision is limited to a point when the cosmos was already 380,000 years old. Before that, the universe was hotter than the surface of a star. This extreme heat meant that light couldn't travel freely across vast cosmic distances to reach our telescopes. Instead, what we observe is a faint background radiation, the CMB, a cooled, microwave echo of the toddler universe, stretched and diluted by billions of years of cosmic expansion. All the really juicy cosmological secrets are locked behind this radiant barrier. We may never directly witness the events hidden beyond the 380,000-year mark. But new research suggests indirect methods might unlock some of that information. Two recent papers propose innovative approaches to glean data from this obscured era. The first study focuses on the potential of faint X-rays to provide clues. While the Big Bang is often portrayed as a singular, massive explosion, the reality is more nuanced. It wasn't an explosion in space, but rather a rapid inflation of space and time themselves. Within this early universe, density fluctuations could have triggered localized pocket explosions or bursts. These bursts could have acted as seeds for things like the supermassive black holes we see today. But they also would have unleashed a cascade of elementary particles. And this is the part most people miss. Because particles appear in matter-antimatter pairs, these burst regions would have teamed with electrons and positrons. When these particles interact, they produce X-rays and other high-energy photons. Most people are familiar with the CMB, the cosmic background of microwave radiation. But there's also a cosmic background of X-rays. But here's where it gets controversial. Unlike the CMB, which originates from the Big Bang itself, the cosmic X-ray background primarily arises from various astrophysical processes occurring much later in the universe's history. However, the cosmic X-ray background is a relatively uniform field of lower energy, soft X-rays. The X-rays generated by these early cosmic bursts would manifest as distinct peaks or anomalies in the X-ray data. With the aid of more advanced X-ray telescopes and extended observation periods, we might be able to identify and study these telltale peaks. Do you think future X-ray telescopes will be powerful enough to detect these subtle signals? The second paper investigates another consequence of these early cosmic bursts. In addition to the surge of matter and antimatter, these bursts would have generated high-energy neutrinos. Neutrinos, famously, interact only weakly with ordinary matter. Because of this, they could have escaped the cosmic light barrier much sooner than photons. We've observed this phenomenon before. For instance, during supernova 1987A, a burst of neutrinos emanating from the collapsing core of the star reached Earth slightly before the light from the supernova itself. The neutrinos were able to break free from the core before the full supernova explosion had even occurred. Similarly, if bursts occurred shortly before the 380,000-year wall, their neutrinos could have escaped relatively unimpeded. By observing the cosmic neutrino background, we might detect spikes in neutrino activity lacking any identifiable astrophysical source. These unusual neutrino signals would stand out against the more diffuse neutrino background. It's an intriguing concept, but it faces a significant hurdle: our current inability to observe the neutrino background with sufficient detail. Neutrinos are notoriously elusive, and while our detectors have detected cosmic neutrinos, we capture only a small number at any given time. And this is the part most people miss. The sheer difficulty of neutrino detection makes this approach incredibly challenging. But humans are resourceful. Who knows what groundbreaking technologies future astronomers might develop? Exploring these ideas is worthwhile because of the immense knowledge we could gain by peering beyond the Big Bang's veil. What revolutionary technologies do you think will be necessary to study the cosmic neutrino background effectively? Could this approach potentially rewrite our understanding of the early universe? Reference: Stodolsky, Leo, and Joseph Silk. Positron signal from the early universe. Physical Review D111.12, 2025 L121304. Reference: Stodolsky, Leo, and Joseph Silk. Signals of bursts from the very early universe. The Astrophysical Journal 992.2, 2025 197.